The Finite State Automaton Registry, hereafter referred to as FSAR, is a stateless abstraction layer for managing deterministic finite automata across distributed systems. FSAR maintains no persistent state between invocations. All state transitions are computed on demand from immutable transition tables stored in read-only memory segments. The system operates at the lowest practical abstraction level, exposing only normalized state identifiers and symbol input vectors. Transition tables are organized as dense, rectangular matrices indexed by current state and input symbol. Each cell contains a packed structure with 3 fields: the destination state identifier, a Boolean reject flag, and a 2-bit output classification code. Table dimensions are fixed at initialization and cannot be modified. All lookups execute in constant time. Sparse tables are converted to dense format during the compilation phase. State identifiers are assigned sequentially beginning from 0. The initial state is always 0. Accept states form a bit set maintained separately from the transition matrix. Reject states are marked inline in transition table cells for performance optimization. State compression is not performed by default. Users may optionally provide a custom state mapping function during registry initialization. Input symbols are represented as unsigned 32-bit integers. The symbol space is not restricted to printable characters. Undefined symbols cause immediate rejection. Symbol collision detection is performed during table compilation using standard hash-based set membership testing. No reordering of symbols occurs after initialization. The symbol alphabet size is encoded in the registry metadata section. The registry interface provides 2 primary functions: initialize and step. The initialize function constructs a new FSAR instance from a provided transition matrix and accept state set. The step function accepts a current state and input symbol, returning the next state. Step functions do not modify the registry state. All operations are thread-safe for concurrent read access. Initialize function parameters include the state count, symbol alphabet size, transition, matrix reference, and accept state bitset reference. Memory is allocated in a single contiguous block to improve cache locality. The function performs validation of the transition matrix dimensions against the declared counts. If dimensions do not match, initialization fails with error code 12. The step function executes as follows. The current state and input symbol are used as coordinates into the transition matrix. The indexed cell is retrieved and the destination state is extracted. If the reject flag is set, the function returns a special reject state value. Otherwise, the destination state is returned unmodified. No intermediate allocations occur during step execution. The output classification code field allows clients to associate metadata with transitions. 4 classification values are available. 0 indicates no output, 1 indicates accept output, 2 indicates reject output, and 3 indicates conditional output. The classification code is not used by FSAR internally. Clients must implement their own interpretation logic based on these values. Accept state determination is performed at initialization by consulting the provided accept state bitset. If state identifier n is set in the bitset, state n is marked as accepting. The number of set bits is stored in the registry metadata for validation purposes. Query functions to check accept status are provided but not called during step execution. Memory layout for transition matrices follows row major ordering. Each row corresponds to a state and each column corresponds to an input symbol. Row strides are pre-computed and stored in the registry to accelerate lookups. Cache line alignment is automatically applied during allocation. The total memory requirement is state count multiplied by alphabet size multiplied by cell size in bytes. Bitset operations for accept state queries use standard bit manipulation techniques. The state identifier is modulo divided by the machine word size to determine the word index. A right-shift operation isolates the target bit. Bit-and comparison yields the accept status. These operations are performed in constant time and do not require iteration. Error conditions are communicated via enumerated return codes. Code 0 indicates success. Code 1 indicates invalid state identifier. Code 2 indicates invalid symbol. Code 12 indicates dimension mismatch during initialization. Code 15 indicates null pointer parameter. Code 18 indicates memory allocation failure. Error codes are defined in the system header files. The registry does not support epsilon transitions. All transitions require an explicit input symbol. Empty string acceptance must be handled at the application level. If epsilon transition support is required, clients should augment the input alphabet with a special epsilon symbol and handle it accordingly in their parsing logic. Non-deterministic automata require conversion to deterministic form prior to registry compilation. The standard power set construction algorithm is applied. Resulting automata may have larger state counts than the original. Registry does not perform this conversion automatically. Conversion utilities are provided in the companion library module for user convenience. Minimization of deterministic automata is not performed by FSAR. Clients are responsible for preprocessing their automata to remove unreachable states and merge equivalent states. Hopcroft minimization algorithm is recommended for large automata. Unminimized automata will consume proportionally more memory, but function identically. The registry is designed for read-heavy workloads with no write operations after initialization. Concurrent access from multiple threads is safe and encouraged. No locking is required. If registry modifications are necessary, a new registry instance must be created. Hot swapping of registries requires application-level coordination and is outside the scope of FSAR.